First is isotopes. Isotopes are when atoms of the same element might have different masses. Like, for example, element X, let's just say, might have a mass of 12. This means I have 6 protons, 6 neutrons. But an isotope of the same element could have 13 mass, and it would have 6 protons and 7 neutrons. That's pretty weird. Well, let's also remember how we write this out, as shown here. Let's take, for example, carbon. The mass number is 12, and the atomic number of protons, the number of protons is 6. And so we write it out just like this, 12, 6, C. Now that's important for later. So today we're going to be learning nuclear reactions. Where do they happen? In the nucleus. And there's 3 different kinds of nuclear reactions, and that release different types of radiation. And we're going to learn about those 3 types today. The first type is alpha radiation. It is shown with this little Greek little letter A. It's the weakest type of radiation from the 3 that we're going to be talking about today. And it is written like this. It has a mass of 4 protons. It has 2. So that's the same as helium. So we write helium right here. Let's look how this could be in a problem. 236, 88. That's mass number. That's atomic number of Ra. The reaction happens. It releases alpha particle. It's called alpha decay. So you have 4, 2, helium. And what's left? Well, 236 minus 4 is 232. 88 minus 2 is 86, and you get Rn. Now that's the first type. Next is beta. Beta reaction or beta decay is shown with this symbol, which is kind of a B with a tail on it. It has the medium strength of the 3 we're going to be talking about, and it's written like this. 0, -1, E, because 0, -1 is pretty similar to an electron, so we write an E. Or you can write it with the symbol B. So there's 2 different ways that beta decay can happen or beta reaction can occur. Beta particle can be released. So let's take an isotope of C, of carbon. It could release, and then it would turn into nitrogen. 14, 14, 6 minus 1, 7. Now that's how you get it equal. 7 minus 1 is 6. Or it could be a beta capture. It's just called an electron capture. So let's say we have aluminum, 26, 13, plus, the beta particle, and then you come over here, 26, then 13 minus 1 is 12, so then you get magnesium. The last type of nuclear reaction is gamma. This is very different. It's the strongest type, has no mass, no charge, no change happens, and it's written with just 0, 0, and then the symbol, which is this weird Y thing. So let's take, for example, this equation. 9943 of Tc. Now you're probably wondering, what is this M? Well, that means that it's metastable, which means that it's probably going to have a gamma ray released, which is just energy. So you have 93 and 43 Tc, and then what's left? The gamma rays, and that's released. Now let's take a look at a visual representation of this. Now let's just pretend that this is paper, this is aluminum, and this is lead. Now if you have an alpha ray, it will go to the paper but not through it. If you have beta ray, it will go through the paper but not through the aluminum. And if you have a gamma ray, it can go all through paper, aluminum, but not through lead. And that's just how you can see that this is the weakest and this is the strongest. So now let's talk about half-life. Well, every single element has a half-life. A half-life is how long it takes for an element to decay into half the original sample. So if we look at this, if, let's say, element X, just for example, has a mass of 10 grams, after one half-life, it will have 5 grams. And every single element's half-life can be different. So let's do an example of what it might be in a problem. So it might say that element X is 10 grams and it has a half-life of 5 years. How long will it take to get it to 2.5 grams? Well, that's simple. All you have to do is count how many half-lives. 10 divided by 2 is 5. 5 divided by 2 is 2.5. 5 years, 10 years, that's 10 years, 2 half-lives to get it to 2.5 grams. There's also a formula that you can use if you have bigger numbers or don't want to use the logic way. There's this formula y equals a 1/2 x. Y is the final amount, a is the starting amount, and x is the number of half-lives. So for example, for this one it would be 2.5 grams is our final, 10 is our original, 1/2, and 2 half-lives. Now the next thing we'll be learning is, so now let's move on to fission and fusion. Fission is when an atom splits up into two daughter products because the nucleus is very large and unstable. This comes in a chain reaction, so it'll just keep on happening and more daughter products will come. It's an exponential process and it has a lot of heat and energy. This means it can be used in fission bombs, power plants, and then the way that they control it is with these things called control rods because it's so exponential. But the only downside is that there's a lot of toxic waste. Now with fusion, it's when two nucleuses that are smaller combine into one big nucleus, and that releases a lot of energy. In fact, 3.5 times more energy than fission. This happens at very high temperatures that we cannot contain. Happens on stars, has less waste, actually pretty much no waste. And how this works is on stars is two hydrogens will combine and make an isotope for hydrogen, and then they'll combine with another hydrogen and make another isotope, and gamma rays will come off, and it creates a lot of energy. In fact, 1 cup of water, the amount of hydrogen in 1 cup of water, could power the whole entire Earth for 1 year. And that's fusion can also be used in H-bombs, which are really powerful bombs. Now let's review. Remember we learned about alpha, beta, and gamma, and how this has the least amount of energy and this has the most. And remember that the equations have to be equal. X equals X. Make sure that both sides of the reaction are equal, especially with these alpha particles. We learned about half-life and how y equals a 1/2 x, final amount, starting amount, and remember that you can also use logic just to find your answer. We learned about fission and power plants, where a chain reaction splits up elements. We also learned about fusion, which happens in stars and combines elements and creates lots of energy. And that's nuclear chemistry for you.